はい、神楽水俣です。苗場の近くだってください。和田小屋。神楽水俣です。神楽の峰っていうのはね、ここ行かないかな。謎吹きが出てね。サマーギャランティ。神楽サマーギャランティ。8000円ディフト代。
So that's going to be the attempt. But again, when these wiggles, they keep telling you about these wiggles, it's all about the interactions, interplays of molecules against, say, one carbon across another carbon chain, or things really close to one another. If you can widen the window to tell you about stuff that interact really close, if these atoms are very close to one another, the more wiggles that tells you more spatial information about nearest neighbor atoms and how they interact with one another. So if you open that window up and use more energetic X-rays, it tells you more about the structure of the molecule. That gets you a better feel for what the molecule is actually doing. In another case, we're going to look at other interesting biological molecules and methylmorpholine. I talk about not enough time in this talk to tell you about it, but they're quite interesting structural dynamics. And again, when you start small, and like again, Rome wasn't built in a day. When you start small, these molecules help feed these powerful algorithms to get us to where we need to look at the biggest structure molecules, really interesting things like peptides and proteins. And then LCLS2, tell you all about LCLS. It is an absolute joy. It is just crazy to look here. Look at the type of science that we can see.
これ覚えとかなきゃいけない。最終19時これでいいんだよ。これが今日はちょっと空が悪いんでね。夏のドロッチちょっと。
LCLS2 will open that capability up to put 1 million laser pulses. This type of statistics with a number of shots.
三つもドロッチ。
A lot of pulses in a short amount of time. It's going to be changing. So you're going to see a lot of construction going on here, starting soon. And 2020 is hopefully when we turn on. So just imagine all the type of science. So I think I want to lay the claim as saying this is the first mention of LCLS2 maybe. So maybe in 10 years' time, we'll come and someone will show my picture up there with. Someone talked about LCLS too. With like any good scientific collaboration, it takes a village, and because there's a lot of working parts. And first and foremost, we collaborative, like our PIs are Peter Weber and Jerry Hastings, the advisor back at Brown, and coupled with a great grad student, James Budars, finishing up the last result of the lab on another molecular movie using diodobenzene. That data is coming out. So we'll be published that soon. Another molecular movie using similar type of reaction or a similar type of technique that we use. And we had Jerry Hastings was a great guy here with he works at Slack and he was I think one of the reasons why I got a look from my boss. I think Jerry said, "You need to check this guy out," and so I owe him a lot. And then guys in the audience, Daniel Ratner, TJ, Joe, these guys were instrumental in terms of how to analyze the data and set up the optical lasers, so couldn't have done it without them. And then lastly, our CGI specialist. It's this is our George Lucas. Adam Kierender is professor at University of Edinburgh, and he was developed the algorithms and the ways to look at these molecules as they evolve, kind of in this big black box computer, and it was able to really put motion to our molecular movie. So I couldn't have done it without him. So I thank you again for your attendance and your interest in our nice little molecular movies. So thank you.
Mike, thank you very much. We have time for questions. So, for the questions, this is being recorded. So wait to be called on and wait till you have a microphone and then ask your question.
Okay, I'm just wondering, you taking pictures in such short amount of time and using such high energy, will uncertainty principle play any role there?
Kids.
Yes. Yeah, because you can never know the position of, say, an electron with respect to time. Absolutely. So there is definitely some smearing and quantum mechanical things on these molecules.
My chemistry is really rusty. So when there are bonds between atoms, there's energy that's manifested in that bond, and what you're showing is a bond breaks, and a very small but finite time later, another bond is reestablished. How does that energy manifest during that interval between the bonds?
So the bond breaks. As the molecule gets excited by this ultraviolet laser, there are different types of. And that's push too, and this is how the energy is kind of spent through that molecule. So if you use the properly tuned optical UV laser light, that you don't whack it so much the molecule just blows apart. You get it just kind of like you just tune it just a little bit and get these bonds breaking. You can easily, reliably control how much energy you put in and how this molecule then can unravel. If you put in a lot of optical laser light, you'll blow it up.
May I call that kinetic energy of a sort?
Yeah, absolutely. It's internally converted energy. Yeah, and so the molecule absorbs. You can call it. Sure.
なんかリスが
Oh, sorry. I sort of get X-ray crystallography, right, when things are solid. I really don't get how you can
because
国の里。結局金にならんといけない。谷川連。
So if you can tee the molecule up perfectly, then the molecule will see the laser light purely, and you'll have a good degree of alignment. But in some cases, the dipole moment could be a little bit skewed. It's locked in like a cloth product, it's called.
Mitsumata Propway.
Pioneered by just this type of cycloactive ringlet thing. There's also rotations about double bonds, building molecules acting like molecular switches. These are all types of ring opening type of classification that that's made. Bench chemist, the physicist got a hold of it, and it's good.
Would you hazard a guess on how long it'll be before you'll look at photosynthesis?
Already being looked at, absolutely. And so there are two. They are very close. I don't know. I'm a betting man, and to think what they're trying to do is track like photosynthetic cells. Watch this around this manganese.
緑を見ると金が貯まるそうです。知らないですけど。
If I were a betting man, which I am, I guess whoever
あっちにもあるな。
is gonna win a Nobel Prize, and that will be done here. I'm gonna hazard a guess, Mike.
I'm curious about the computational requirements for what you're up to. This is picked a rather simple molecule for good reasons. Have you forecasted what computational requirements are going to be necessary as you go up to try to get at proteins? Or
Huge.
なるほどね。
Proteins are huge. I have no
めっちゃ遠いなこれ。和田小屋こんなとこある。 神楽の海でこんな遠いやん。
I'll forget. I'll think of it. I'll think of it a bit. This is where these large superconducting cluster or these cluster
車で20分。
these calculations will run. Up the road here in Berkeley, NERSC is a huge computational facility, and to run something on the order of peptides and proteins that have hundreds of more electrons, many more electrons, it just scales non-linearly. So it's a very an exponential growth and then not a mound of computation. Now, I have no good grasp. TJ possibly could
These
tell you.
are already petascale computations to do the movie that we saw.
I didn't hear that.
These are already petascale.
Yes, many.
To do the movie that we saw.
Yes.
I just hate to have you be able to take the pictures but not calculate the motions.
They go hand
Not
in
much.
hand, that's for sure.
Hi. この間ここに登ろうとしたの。
Looking at it as a chemist or a physicist, whereas a liquid bench chemist might look at it as a 50% of the time. One, it's our resolution, and so right now, in all the trajectories that we see and that we were able to compute, about 60% of them open and about 40% of them don't open. If we get the spatial resolution that we're seeking to know the nearest neighbors better and those distances better and all the length scales across how each individual atom occurs, I think the picture will become more clear. At the same time, the way we also increase spatial resolution is we limit the amount of molecules that the X-rays can see. So in the case that I showed you today, the X-rays went through a vessel. Remember, we saw this green bubbly vessel with the cyclohexadiene kind of bubbling through there. To put some length to that, there was about 13 millimeters, or about the size of a penny. And so if you imagine the X-rays that are super small, 10 billion of a meter, as they zoom through this penny-sized vessel, it can interact with many atoms. Or I'm sorry, many molecules on the order of like 10 to the 12, many million molecules. Well, the case is when they detect when they get detected by the detector, where they're generated along that penny length, to smear out where that wiggle is detected that tells you about the distance. So if you sharpen that line up, if you try to work to the idea of having one single molecule interact with the X-ray beam, that's where you need to go. People are doing
Minami Ichigo Kankou Bus.
So I imagine a practical application for this ultimately might be in pharmaceuticals or material science. So how far away we are from using molecular movies for this?
Sure. I would say not far. I mean, like we already saw, there were some. We looked at how molecules in our brain can signal one another, and so these type of reactions can be probed. There was a recent result that I didn't show, talking about the structural changes of how arrestin interplays. There was a really big, nice paper. So that's how drugs are kind of actively delivered in modern-day pharmaceuticals. And so we can study those molecular changes. In terms of material science, it's already done here. But in terms of molecular movie, I don't believe there's anything done on that type yet. For an example, we can look at novel materials that potentially be superconducting materials. So this is like a lossless way to put electricity from one side to another across these really couture, very custom materials. And if you pump it with a different type of laser, you can watch like these channels form and let these electrons flow freely. We could do that now, and so that's a material study that we can do. Yeah.
Are you planning to do like these studies on like amino acids and how they come together to form a protein?
That would be an absolutely great question. So if you didn't hear that, was like, can we watch basically a chemical reaction occur? And that is my hope, to watch if you can envision a liquid jet of one protein and a liquid jet of another interact in one area.
Mukayama. Are they Mukayama?
That would be killer. That's a great question. And yes, I think there can be recombinant sources that can put two reactions together to make a product form. I think we can do it. Time frame, LCLS will make it hard, but LCLS2 would make that a little bit easier of a measurement because you have more X-rays coming in 1 second, so you can.
この辺雪深いんでしょうね。
What about like the amino acids like bonding
一番でもない。
with each
北海
other
道
to
はある
make
から。
the peptide?
Yeah. Yep. Not yet. We haven't seen that yet, but I think in these type of reactions or those type of reactions in the future, short time, well within your lifetime.
ならず山。
Okay.
You got your mic.
I finally got it. Okay. My question is this. If you care about molecules and vitamin D, what is happening if vitamin D behaves kind of the same way? What is the change in function that results from the fact that you start with a cyclic, a benzene ring or something like that, and you end up with an open one?
this
계산
bond
코스
breaking,
ある
if it did not break, what would happen?
これぐらいいけそうだな
Oh,
めっ
sure,
ち
sure,
ゃ
sure.
長えなここ
So I'm gonna, like the gentleman said, his chemistry was a little rough. My biology is easy. And so, so basically,
ここ山で10キロある
次食べて、普通に飲めば OK だい。だっていいやられるじゃん。私そうでなくてもさ、胃潰瘍があって痛い痛い病やってるじゃん。あ、疲れた。
pocket of electrons localized around this ring. Pop it open and it's like a wire. Charge flow. So it's charging. I believe. I would have to look. I'll get back to that.
私がどっかに
But I believe it's
どっかに
something close to that.
ドライの女子着替え買ってください。
It could potentially rotate about this bond. Would it serve the same functionality? I don't know. But in terms of there's enough energy in the bond being broke, and this molecule able to flop around, yes, it could rotate. Now, how that plays with the biology of what's happening in our body, I have no clue.
So you had you only saw a 60%. Would you say?
That result wouldn't rattle the world. It wouldn't make it make us come to a stop. It would make us rethink type of gas-phase chemical reaction dynamics. Stuff that potentially could happen like in the atmosphere, or how hydrocarbons react, and functionality. But in terms of, since there are already some good error bars on it already, 95%. Reaction actually progresses through nature, but it wouldn't make this work.
Thank you for taking a second question. You described the scattering and the rings that were created. You had to validate. How much of that is done through discovery, or did you shoot multiple molecules of known geometry and compare the outcome?
Good question. Very good question. There was some black magic to this. Like we said, there's good CG. But let me slide that wiggles, right? That's right. So if you have, you're talking about these type of, with these rings here, what you're saying on the pattern. Sure. So, in how to capture and catch these X-rays that scatter off these cyclohexanide molecules, we need to know how far a detector away is. It tells us how the detector panels, like a CCD camera, how they interact and talk with one another. So we use a molecule, before we started taking cyclohexanide, we used a well-known molecule called sulfur hexafluoride. This molecule, so it's a sulfur with 6 chlorine atoms hanging off it. This has been used, and the structure of this molecule is known with many, many, many more wiggles than this. And so for synchrotron days, you can sit there, there's a lot of electrons, it scatters really well. So when you see this pattern emerge from a known structure, you can say, all right, I know on this part in my detector that gives me a distance of like 2 inverse. So that's how we physically calibrate the system in terms of space. But there are computational programs out there that you say, all right, I want to measure what the pattern of this molecule scattered, like the X-ray pattern, the billiard pattern, what this is going to look like if just by itself. And you can do ways, you can put motion to it too. This is called time-dependent density functional theory, and all these different type of quantum mechanical ways to look at this molecule in a computer. We did play with those too, for sure. So we needed to see the structure on the screen. Once we analyze that data, see the data out, like, do we have it or we don't have it? And if we don't have it, why? And if we do have it, then send up a rocket and we're happy. And so thankfully the latter happened. But yeah, so it's a good play in terms of, we do use some calibrants first before we get to the nitty-gritty.
背中になんか書いてあるよこれ。見て見て。書いてない？書いてない。あ、ここだけか。
I'm trying to do the math in my head, but if you say the wavelength of the ultraviolet light is about 1 nanometer,
no, about 267 nanometers.
Well, and your pulse is 1 femtosecond, so how many wavelengths is that? It's almost down to 1 wavelength or something like that.
Oh, okay. The difference between the wavelength of a femtosecond is a micron. Yeah. You still got about 300. So the UV light that shined, that excited the molecule, had about 260 nanometers. No. So,
So we'll be around here for some time if you want to come down and ask more questions. Also, the people running the microphones are from Mike's group.
So we're going to get going. So it's my pleasure to introduce today's speaker, Mark Hogan. To me, Mark has just been a staple at SLAC ever since I joined the lab. To me, it feels like a while ago. I know there's people in the audience who've been here a really long time, but Mark's just a very recognizable figure, and we actually spent some cold, dark nights together over at the PD area in the early 2000s. Mark earned his PhD from UCLA, and he joined SLAC as a postdoc, and basically been here ever since. And he came here to conduct advanced accelerated research using lab wake field. And in 2000, he became the
It's funny because Dave and I spent a lot of time in the FSTV in the early 2000s, and that's when I was a postdoc, and I remember having a conversation with my wife when I came here to do this work. I thought, well, really, I don't know, it's going to be a few experiments, so I'll have to find a job, but I'm going to walk you through the history of first of all, what it means to be accelerating particles on waves of plasmas, and why we think that was interesting back then, and why it continues to be interesting, and we're still pursuing this work here at SLAC. So first of all, just embracing Chi Chang's challenge that